Welcome, everybody. Okay, this is better. All right, few logistics things. I handed out the handouts already, so please make sure you have a handout. Also, the next project, which is, I believe, project 4. Is that correct? Project 3 is naive Bayes, yeah. So now project 3 is still going strong. I see a lot of submissions. It's very, very nice. Project 4 is, we are still testing a few aspects, and we're talking with Vocarium right now to just make sure everything works seamlessly. So it may be delayed by a few days. So it may be delayed by until Friday. You will get your full 2 weeks, so this is not eating into your time. Also, the CEO of Vocarium just emailed me. He has seen all your complaints and all your suggestions. Piazza, thanks to those who posted something there. They're taking this very, very seriously, and they're very interested in fixing things. So please continue to post things there. They found some bugs in their software, and hopefully most of these things will be addressed very soon. All right, any questions about logistics? The other thing is the exam is just around the corner, by the way. Right? So we have 2 more weeks, less than 2 weeks. So please get started. Please, I just want to remind everybody, the exam is a huge part of the grade. The biggest failure mode in this class is to do really well in the projects, but not do well on the exam. So please take it seriously. Okay, so last time we talked about, question? Yeah, we currently try to find one date where everybody can do it. It may be a Sunday. It's really hard to get everybody in the same room. And yeah, please follow the Piazza posts in that regard. I guess if you miss the makeup exam, then it will end up being an oral exam in my office. So that's kind of the way it works. All right. So last time we talked about the square loss. So the square loss was basically linear regression, where we said we have our data and we make an assumption that the data is somewhat, lies on a line, right? Like it's basically a line is a good model of that data. Or better said, there's a linear relationship between x and y. And then we made a second assumption that, well, of course, the points won't be exactly on that line. So if they're off, we actually assume we have Gaussian noise. So we put a Gaussian around basically this. And this says the probability of being here is kind of a Gaussian center around with the mean, which is the position of that line. We derived this, and it turned out actually this loss function is a parabola. And once we went through all the notions, it just turned out to be quite simple. The loss function was basically just, well, let me write it down here. The loss function ended up just being sum over all points, W transpose xi minus yi squared. And if you do, that's the MLE answer. So this is basically the loss function you're trying to minimize with gradient descent. And the MLE, the map answer is you basically add a regularizer to it. So you have plus lambda times squared. So this is if you have map. Okay, so one thing is this is a parabola. So turns out it actually has a closed form solution, right? So a function that a parabola, we can just find the minimum in closed form. This is essentially actually doing a Hessian update. If you just use the Newton's method and take one step with Newton's method, then actually you get right to the minimum. We can quickly derive this. I just want to spend 3 minutes deriving this. One question that people ask me is, do people actually, if there's the closed form solution, why don't we just always use the closed form solution? Why don't we actually use gradient descent? And the answer is, as you will see in a minute, the closed form solution requires d squared memory. And is actually d³ in complexity. So I'll get to that in a minute, but it turns out that for large enough dimension, that actually is prohibitive. So let me just derive this real quick. What's the closed form solution here? So let's say I define a matrix X where X transpose is the following: X1, Xn, and Y transpose is Y1, Yn. Right, so X is basically a matrix where every row is a data input. This is exactly the kind of matrices you use in your projects. Then I can write this loss function as, by the way, please everybody close your laptops. Thank you. You can write this loss function as the following. This is just X times W minus Y squared. Right, so that's the loss function if I just write it in matrix notation. Raise your hand if that makes sense. All right, awesome. So I can write that out. And I get xw minus y transpose xw minus y. So that's, so far nothing interesting here. And if I multiply this out, I get the following. I get w transpose xw. That's these two terms. Then I have minus twice y transpose xw. Oops. Plus y transpose y. All right, so this is just completing the square. And this is now my function. This is the parabola. You see basically this here is a positive indefinite matrix. And if we now want to find the minimum, we just take the derivative and set the derivative to 0. Right? We take the derivative of this function here with respect to w. All right, any questions so far? So one more time, I took this loss function, I just write it in matrix notation just because that's cool, right? And then I write everything out in matrix notation. This makes it very obvious that there's a closed form solution. And now I have this function here. This is just the function of w, right? This is a function that tells me the loss with respect to w. If I want to find the minimum, I take the derivative with respect to w and set that to 0, right? This is something you've been doing your whole life, right? And so if I do this, then the derivative of this function becomes x transpose xw, right? This is this quadratic term. This is, by the way, if you're not familiar with taking derivatives like to vectors, please look at the matrix cookbook. It's something that's very, very useful if you're familiar with it. If you're uncomfortable with it, you can always go back and take the derivative with respect to every single wi, right? So that always works. It's just a lot of notation, a lot of summation. So it's actually, it can, when you do this kind of work, it can save you hours and hours of time if you're just familiar with taking derivatives with respect to matrices. Okay, so this is the term you get here. This is because we have w here on both sides. Just ends up being x transpose x times w. Then we get minus 2 y transpose x, and then the w. This is a linear term, so we just get y transpose x. This is the derivative. We set this equals 0. So if you put an equal 0 here, that's the same thing as putting an equal here. Raise your hand if you're still with me. All right. Now we get rid of the two 2's because we don't need them. They're on both sides. And now we have some matrix times w equals something. Well, we just multiply with the inverse of that matrix. So we get w equals x transpose x minus 1. Oh, and sorry, I made a mistake here. This is x transpose y. X transpose y. Okay, I have to transpose it. And that's the solution. So this is actually the closed form solution to this loss function. So if you can compute this, then there's nothing else to be done, right? You just jump right to the minimums. This basically, your function is a parabola, and you can just jumps right here, and then you're done. Why don't people always do this? The answer is this matrix can be gigantic, and inverting a gigantic matrix can take forever. Right? So there's two problems. A, you have to store this in memory, which you may not be able to do. And then also actually inversion is very expensive. In practice, actually, you don't do the inversion. The way actually you can also write this as a linear program. And then you can do it a little faster. But ultimately, the complexity is the same. The complexity is d³. So cubic complexity is always a problem. So what that means is basically if you double your data, it becomes 8 times slower. Right? So that's what cubic complexity means. the complexity is d to the cubed, right? This is the and this is the space complexity. So this is space, and this is computation. Raise your hand if that makes sense to you. Okay, those are the basically that's kind of elementary computer science. The idea is basically whenever you have an algorithm, you try to argue how much slower does the algorithm get, how much more space do you need as you increase your input size. And here this is a function of the number of dimensions that you have. Right, so for example in spam filtering, my canonical example, there you actually have millions of dimensions potentially, because the dimensions are the number of words in the English language. So if you have millions of dimensions, then this here becomes prohibitively expensive. Right? So what you do is you just do gradient descent, and that actually works really well. Any more questions about least squares? Yeah?
Why did you switch from y transpose x to x?
Oh, it's just because when you take the derivative, you have to actually take the a times w. If you take the derivative with respect to w, it becomes a transpose. So that's the matrix cookbook. Yeah. Okay, any more questions? All right. Today we'll do something much cooler. Even cooler than linear regression. Okay, today we'll talk about support vector machines. All right. So, one more time. So last lecture we talked about regression. Let's go take a step back one more time and talk about classification. So our labels yi are this time either +1 or -1. And just as before, we make the assumption that the data is linearly separable. So we have data. We have some crosses, some positive points, we have some negative points, and we would like to find a hyperplane between these two. Now, one thing you already know is if you know such a hyperplane exists, we have an algorithm to find such a hyperplane. Who remembers the name of the algorithm? Perceptron, right? So the perceptron finds us a hyperplane, but you have no guarantee what hyperplane it finds, right? And it turns out actually there's infinitely many, right? If there exists one, there's infinitely many. So you could actually have this one, or this is a hyperplane, or this is a hyperplane, etc. Right? So people have been wondering ever since it was possible to find a hyperplane. The obvious question is, well, which one should I find? Right? And that's where the perceptron is weak. Right? You have no guarantees on what you find. What the SVM does, it actually finds you one, a very specific one, and I would argue that's the one you do want to find. And so if you remember correctly, in the the perceptron proof, what we talked about is we had this notion of margin. We basically said, how many steps you need to find this hyperplane is inverse proportional to the margin. So what you want is the data to be far away from each other. And just to remind you, the margin, if I have a hyperplane, is the distance to the closest point. Right? That's the margin, I call it gamma. And the intuition behind SVMs is that if I want to find any hyperplane, the best hyperplane is actually the one that has maximum margin. Right? That's the idea. So originally, actually, they were phrased as maximum margin classification. And that's not just a good intuition. You can actually theoretically derive that this actually is likely to generalize very well. So the idea is, if I have a hyperplane that's kind of really far away from the positive points and really far away from the negative points, then if my positive points and negative points are drawn from the same distribution, they won't be exactly the same points. Like my test points that I actually care about. When I actually deploy this thing, I'm going to see slightly different points, right? I see maybe this point or this point, right? Hopefully, they will be somewhat in that region where my training axes are. And if I move my hyperplane as far as possible away from these points, I give a lot of margin of error, right? So they basically, if they're here, then that's not a big deal, right? Because I actually have this larger margin in which they could fall into. If instead I draw on the hyperplane like this, which is perfectly fine, it separates the training data very well, but now if a test point is here, it would actually be misclassified, right? And intuitively, that seems like the wrong thing to do, right? Because that point is still very close to these guys, right? Does that make sense? So the idea is if we find a maximum marginal hyperplane, it's actually, that's basically defined as the hyperplane that has the maximum distance to its closest points. And that's always exactly the same on both sides. Can anyone tell me why that is the case? Why do you have the same margin on both sides? One person already knows it. Yeah, sure? That's right. If one side was closer than the other, then let's say here's a little larger, then what I could do, the margin is actually the distance to the closest point. So let's say my hyperplane is this, and this guy is closer than that guy. Well, what I then can do is actually I can, the margin is defined as the shortest distance to a data point. Then I could find a better hyperplane that's moved a little bit over here, right? That increases this margin, right? So by definition, the distance to the closest point in the positive class and the distance to the closest point in the negative class must be exactly the same. Okay, any questions at this point? All right, so SVMs were invented, I think, in 1994 by Corinna Cortez and Isabella Guillon and Vladimir Vapnik at AT&T. To this day, they are the most popular machine learning algorithm and are extremely successful. It's also one of my favorite algorithms. There's one little caveat. It's actually patented, so you're not allowed to use it. But besides that, it's great. But to put it another way, if you use it and you just can't admit it. So there's actually a patent troll company that owns the patent. And if you ever were to admit that you use SVMs in any product that makes money, they will sue you quicker than you can say support vector machine. And actually Oracle, for example, they foolishly admitted at some point, they advertised our databases now have support vector machines, and bam, right, they get sued the next day. But you can always say we're just using learning a linear classifier that has a maximum gap between the hyperplane and the closest point, right? So if you avoid the language a little bit, then it's very hard to prove that you're actually using SVMs. Okay, good. So let me just formalize this notion of margin. We've talked about this a little bit already, but let's just make this crystal clear. So we have our hyperplane. Our hyperplane is the following set, is the data points x equals to w transpose x plus b equals 0. Right? So this is my hyperplane indexed by w and b. So far that should be, that's basically the set of all points that lie right here in this middle. And what I want you to think about a little bit is what is the distance to a point from a hyperplane? And this was, you may recognize this was actually on the placement exam for exactly that reason, because I wanted you to kind of get a little bit of a head start just thinking about the geometry of these things. So let's say this here is my hyperplane defined by the vector w. And now I have some point x. And I would like to know what's the distance from this point x to the hyperplane. And the first thing I can do is say, I can project this point x onto the hyperplane. That's basically this point here. Let's call this xp. And then the distance from the hyperplane to this point is exactly the distance between these 2 points. And we call this vector here d. Any questions so far? Raise your hand if you're with me. All right, good. So one more time, I have this hyperplane this hyperplane defined by w. I have some point x. I would like to know how far away is that point from the hyperplane. What I do is I project the point onto the hyperplane. That's the closest point on the hyperplane to x. And now I measure the distance between these 2 points, xp and x. I call the vector between these two d. So then I can say xp equals x minus d. Okay, so if I take x, I subtract d from it, then I get exactly my point xp. All right? Any questions? All right, so then what do we know about xp? We know that xp lies on the hyperplane. What do we know about points on the hyperplane? By definition, these are the points where w transpose x plus b equals 0. So what we know is that w transpose xp plus b equals 0. Right? That's just the very, very definition of points on the hyperplane, and we know xp lies on the hyperplane. So far, no big problem. Now we can plug in our definition of xp in here. So what we get is w transpose x minus d plus b equals 0. And now comes the question, what is this d? And here's one interesting realization, that d is actually, although I didn't draw it that way, must be parallel to w. Right? So because that actually points away from the hyperplane. What points exactly orthogonal to the hyperplane is this vector w. Right? So actually d is basically a rescaled version of w. It must be, right? Because it's parallel to it. So I can say, instead of d, I can write d equals alpha times w. Raise your hand if you're with me. Awesome. So I just plug this in here, and what I get is w transpose x minus alpha times w plus b equals 0. And that's all I need, because here b is given, w is given, x is given, so the only thing I don't know is alpha, so I can solve for alpha. Right? And if I do this, what do I get? If I solve this, it follows that alpha equals w transpose x plus b over w transpose w. So what I'm doing here, well, I know, maybe I give you a minute to digest this and try to verify this. Any questions? Raise your hand if you want me to move on. Awesome. Okay, good. So my hope was that if you've all done it for the placement exam, then we can go through this quickly. Okay, great. So now we know exactly what alpha is. That means we know exactly what d is. Right? So d is alpha times w. So d equals this term here. Alpha times w. Alpha is w transpose x plus b over w transpose w times w. Right. And that's basically, that's a scalar. That's my alpha. And that's my w. All right, so now what I want to know is what is the length of d, right? And that's basically what I have to compute is what's the norm of d. So the norm of d equals d transpose d and the square root thereof. And that equals, well, okay, so I guess I have it in here. Actually, let me write it down. Alpha squared w transpose w. Because d is alpha times w. So this here is alpha squared times w. People nodding? Maybe you just nod. I don't have to raise your hand all the time. This is some vigorous nodding. Okay, good, thank you. You take the alpha out. Right? It's an alpha squared. You can pull that out. And then you get square root of w transpose w. Now what is this? Well, what's alpha? One more time. That's this term up here. That's my alpha. So it's w transpose x plus b over w transpose w. That's my alpha. Times the square root of w transpose w. Okay, one more time. I take my D, I have my formulation for D. I want to know its norm. Norm was just the square root of its square, vectorized square. Now I plug in the definition of D, which is alpha times W squared. Alpha times W, I square the whole thing, I get alpha squared times W squared. I pull the alpha out, I get alpha times the square root of W transpose W. And now alpha is this term here. If I multiply that with the square root of W transpose W, I can just divide by it, and this term disappears. And that's ultimately what I get. So it is W transpose X plus B over the norm of W, which is what? This here is the norm of W. So this here is the distance of a point X to the hyperplane. And if you remember this from geometry, when you went to high school, that's exactly the formula you learned. Any questions? Ready to move on? Question or ready to move on? Okay, question, yeah.
So this is in L2, and if we go to other metric spaces, does it break and become impossible? Are there certain spaces that work? Is it just more complicated?
It works in all the spaces we care about. Yeah. I mean, it doesn't have to be. Oh, sorry. I mean, this is just the. It just has to be this is Euclidean spaces. So it doesn't have to be two-dimensional or something, right? This can be n-dimensional or d-dimensional. That's totally fine. And it also works in general Banach spaces, etc. And this will become relevant in a few lectures. Good question, though. Yes. Any other questions? Okay, awesome. So now, this is the distance to a data point. Well, we want to know the smallest distance to a data point. And so we can just define the margin of a hyperplane defined by W and B is the smallest such distance, so the smallest W times X plus B over the norm of W. Right, so that's basically you go over all the data points in the data set, and you compute the distance to the hyperplane for every single one of them, and you say, what is the smallest one? Right? Which one has the smallest distance? Okay, maybe take a second and digest everything. All right, any questions? All right. So what an SVM does, it says, well, a second, right? So we can define this is basically the formula of the margin of a classifier, this gamma here. And what we would like to know is the hyperplane that has the largest margin, right? And this is what the margin is. So why don't we do exactly that? Right? Why don't we just say you want to find the W, which maximizes W comma B, right? Gamma of W and B. So this basically says you want to find the W that maximizes the margin. So if we just leave it as this, what do we get? All right, so maybe I'll give you a minute to think about it. So are we done at this point? We just say, this is my optimization problem. I just want to find any hyperplane WB which has a maximum margin. So I'll give you a minute to think about it with your neighbor. Why is this going to blow up in my face? All right, who knows? So if this is my data set, I'm trying to find the hyperplane that maximizes the margin. Where should I draw the hyperplane? What is my optimization going to give me? Yeah? You could draw it here. That's right. Right, so if you want to maximize distance to your data points, you're just going to go push it away to infinity. Right? And that's a great hyperplane, really large margin to both classes. Right? But that's not what we want. We want a hyperplane that actually lies in between the two classes. Right? It's actually separated. So we have to somehow force this maximization to also do something sensible. And we do this with a constraint. So this goes into constraint optimization problem. So in constraint optimization, you basically say, well, maximize this function, subject to a certain constraint. So the following has to be satisfied. And the constraint is that for all our data points I, we have to have that yi w transpose xi plus b must be greater or equal 0. And so we had this before when we talked about the perceptron. This here basically says which side of the hyperplane you lie on. Right? If you're positive, on one side you're positive, on the other side that's negative. And if you multiply with the label, the positive points, if the positive points are on the positive side, then that's positive. And if the negative points are on the negative side, that's also positive. So if this constraint is satisfied for I, then you must lie between them. And then actually we get the right classifier. Any questions? Yeah?
So those have this other constraint that the minimum I has to be equal to 1.
Ah, you're looking ahead. I'm not there yet. Right, good point. So we'll get there very, very soon. All right. So we want to solve this. Right now we don't yet know how to solve this. Right? And so this is actually where we will get to in a second. So we know we want to maximize this function subject to this constraint. And now just pay attention for 5 more minutes, right? Then we are there. It's only like 3 steps. So you're going to learn something really, really cool. Being able to solve these things makes great conversation pieces at first dates, cocktail parties. All right, so now you plug in the definition of gamma, which is basically just saying you want to find, here you want to find the, the minimum x element of D, W transpose X plus B over W transpose W. Actually, this is the absolute value. Okay, so now we have something really nasty, right? Oh God, you're going to put on sunglasses, right? It's going to protect our eyes. It's a maximization of a minimization, right? It's nasty, right? So let's not be scared. Just keep going. What can we do? Right? The first thing we can do is we can pull this W transpose W out of the internal minimization. Right? You have a maximization of a minimization, but W transpose W here is not actually a function of X, so we can pull that out. So we pull that out, sure, why not? W transpose W. So now we just get this term here. So we minimize W transpose X plus B over X, and then we multiply the whole thing, maximize that over W. That's still pretty scary, right? But now comes the cool trick. And the cool trick is that if you have a hyperplane, right? So this here, my hyperplane is defined up here, but this is my W, right? My set is all the points such that W transpose X plus B equals 0. What I can do is I can multiply my W and B by any constant, right? And it doesn't change a thing. Okay, does that make sense? So if I take this equation here, W transpose X plus B equals 0. If I rescale W and B by any positive value, it makes no difference, right? It's going to be exactly the same set. So what I'm doing essentially, I'm just rescaling this vector here, W, right? I can have infinitely many scales here. It's always exactly the same hyperplane. So that's a degree of freedom that we can utilize. Okay, so currently there's no unique solution. So we don't care which scale we get. Right? It doesn't really matter. We just want to find the separating hyperplane. So we can just fix a scale. All right, raise your hand if that makes sense. All right, awesome, good. So let's just fix a scale that's really convenient to us. And here's the scale we're going to fix. We're going to say, okay, well, we want a very specific scale such that the minimum W transpose X plus B, or actually it's just this. Well, yeah, okay, minimum equals 1. Right, so you just say we just rescale it exactly in a way that this here is 1. Right? It's a good trick, right? So now this whole thing is just 1. And so now we are left with just, the maximization of 1 over W transpose W. Right? And we just have one more constraint. Let's not talk about this. So, so the objective function is now much, much simpler. Okay, any questions? So we still have to deal, we have committed some sins here. We still have to deal with this constraint in the future. But for now, just we basically pushed it down as a constraint. Yeah? Well, because there's always, I guess, if I give you some x and b, right, I can always rescale this in any way such that the minimum, the margin is exactly 1. Right? Like whatever your margin is, I can just divide my w and b by exactly that value so that this term is 1. Right? It gives me the same hyperplane. Doesn't give me the same solution to the problem, but I don't care about actually the actual value of this problem. I care about the hyperplane, right? And for my means and purposes, that's identical. Does that make sense? All right, good. So now we get rid of all this scary stuff, and now we have 1 over W transpose W, right? Now here's a very important lesson that you learned last time, right? Maximization is for losers, right? We want to minimize. So let's put a minimization here. Right, and we just, just say instead of 1 over W transpose W, we just minimize W transpose W. That's actually the same thing. There's no difference, right? You can either maximize X or minimize 1 over X. It's the same thing. Okay, good. Raise your hand if you're still with me. All right, okay, good. So now we're almost there. Now we just have these two constraints. And so now I claim something, and I want you to verify it. That instead of these two constraints, right, we can actually write something else. We can write, instead of these two constraints, we can actually write, that's the case if and only if, for all I, yi, W transpose xi plus b is greater or equal 1. So I claim that this set of constraints is identical to these two constraints. In particular, these two constraints, if they are satisfied, implies this. And if these are satisfied, it implies these two. And I give you a couple minutes. Please talk with your neighbor about it and see if you can prove it. That's actually exactly the same thing. All right, who can go one direction or the other? Left to right or right to left? Who is brave? Nobody? All right, Arthur, right?
Yep. So basically the argument is that if your minimum is equal to 1 and everything else is greater than 0, then everything's just greater than 1.
Okay, good. That's right. So this is from going this direction to that direction, right? But he's saying everything is greater equals 0. You have to be a little careful, actually. So everything here basically says has the right sign. It's on the right side. So what I can do is I can actually rewrite this thing here as yi times this, right? Instead of the absolute value. Because that's the same thing, because I'm basically multiplying with the same sign that's here. Otherwise, this would be negative. And then I actually know that the minimum here is 1, right? Therefore, they must all be greater or equal 1. That's another way of saying it. Okay, raise your hand if that makes sense. Okay, good. Any questions? There's some questions, yeah? So in this case, actually, you're just going from left to right. You're just saying the fact that everything is, the minimum is 1, must mean that everything is greater or equal 1. So that's just going from left to right. I think what you're concerned about is the other way, right? You're saying going from right to left, it could be that the minimum is actually 5, right? Which is still greater or equal 1, so everything here is satisfied. But we are violating this guy here, right? That's your question? Okay, good. So left to right, everybody's okay? Left to right, tick. Okay, now right to left. So assume this here is satisfied for every single data point. Now he's raising a very, very good point, right? He's saying, wait a second, assume for every single data point, this expression here is greater or equal 1. Well, it could be 5, right? Or it could be 100, right? The smallest one could be 100. So then this here is definitely satisfied. Everything is, greater than 0, greater or equal 0. So we're not worried about this constraint. But this here seems fishy, right? Here we're saying very explicitly, the smallest margin has to be 1. And here we're just saying it has to be greater or equal 1. So it could be larger than 1. Why is that not an issue? Who figured it out other than Arthur? Yeah? You could, and why is it going to be downscaled? Why is it going to be exactly 1? Yeah? That's right, because we are minimizing W, right? So if you had something that's larger than 1, let's say you have 10, right, for the smallest one, and every single one of them is larger, greater or equal 10, then what you could do is you could actually reduce your W further, right? You could just actually divide W and B both by 10. Your constraints are still all satisfied, but you're getting a smaller objective value, right? And therefore, it can't be the optimal solution, right? So in the optimum, this implies that, right? Does that make sense? That argument make sense? So the key is, because we are minimizing the square of W, we are fine. Any more questions? All right, so the good news is, this problem on the right actually is a quadratic function up here, right, before it disappears. This is a parabola, and this is a linear constraint. That's a quadratic program. And quadratic programs is something that our friends in the math department have been studying for 50 years, right? So they've written all these packages in obscure languages that nobody uses, to minimize these functions. And we can use them or write our own.
Real quick.
Yeah.
Last lecture, you said you were going to start with a demonstration, and I completely forgot about it until you brought down the projector.
All right, I owe you another demo. You called my bluff. I made up that demo. But no, I do actually have one. All right. All right, thanks for keeping me honest. Well, let me first do the demo for this class, and then we can still do the other one. Why is there banana? I don't know. Okay, So here we go. So we have a data set. So we can now create a data set. Let me just make some linearly separable data. Oh, shoot. What's going on? Oh, that's good. All right. And here my negative, here my positive points. Or the other way around. And I can now run my SVM solver. And what it will give me is exactly the hyperplane with maximum margin. Right? So you basically see here's the hyperplane. And the white lines are basically exactly the parallels that goes through the closest point. And you can see they're exactly parallel, they're equidistant from each other. All right? And so the beautiful thing is about, you just run this QP solver, this quadratic programming solver, and bam, right? You get the answer. Right? There's no iterative process. I mean, ultimately inside that package you have an iterative process. But it's just such a beautiful formulation of a machine learning problem. Right? So when this came out, and people hadn't thought of machine learning that way. Everyone thought of like some algorithms that iterate over something, right? And then basically Karina Cortez and Isabella Guillon came along, and they just said, well, you can just write this as an optimization problem, and zack, it gives you the answer. And that put the entire field into a frenzy. Like for 10 years, nobody did anything else but quadratic programming, right? Or convex programming. I can show you some. I don't know. Does anyone want to see any other examples? I mean, I guess we can do something where they are really close together, right? That's something where the perceptron would take a really long time. Right, so here we have, very, very small margin. So the perceptron would take a long time to converge, right? But the SVM, bam, right, immediately finds it, right? And so this is what makes SVM so popular. It turns out like when this came out, suddenly they blew everything else away. You get much lower error on most data set, right? And you could actually run it. Like it's such an elegant framework, right? Everybody understood it. Any questions about the demo? Yeah?
So our minimization works on one side, the closest of one class to point. What about the one on the other side? Does minimizing the closest point for one class also minimize the margin for the other class?
No, you're automatically minimizing both, right? Because you're minimizing, you mean the constraint?
Yeah, essentially.
So basically that's the closest point has to be one away.
Yeah.
But by doing that, you have to have equal distance from both classes. Otherwise, you could always move closer to the one that's further away and increase your distance to the closer one. All right, so the other demo, I guess I push that away to next lecture. Please remind me at the beginning.